Okay, so we will look on the scalar quantization. So scalar quantization means that many of the fundamental ideas of quantization and compress are easily introduced in simple context of scalar quantization. So an example is when you have any number of x can be rounded off to the nearest integer. Okay, so this is a simple, okay, how the scalar quantization will be done. Okay, you will have a real number, so you want to round it. So each of the point will be rounded as the nearest integer. So this is how the scalar quantization will be done. So it will truncate all the point numbers, okay, the point numbers to be as an integer. So what you will do, will map the real line R, continuous space, into a discrete space. Okay, so this is how what we've been discussed before. You have the continuous space, then you want it to be in discrete space. Discrete space means it will be a exact number. Okay, it can be considered as integer 1, 2, 3, 4. But continuous space means you can be in a real number. Okay, if you transform a signal, okay, with the sinusoids, so it can be a point form. So we don't want it to be in a point form. So once you do the scalar quantization, it will be in a discrete space. Okay. So the problem of scalar, okay, for example, you have a problem 1. So you have a 16-bit integers. So 16-bit integers, the grade level will be from 0 to 65545. So unfortunately, you only have a space to store 8-bit integer. So which you only have a range of 0 to 255. So this is how the problem comes. So that's why you need the scalar quantization, where you will reduce, okay, a big range of bit, okay, to be in a smaller range. So how it will be done? So it can be done in a scalar quantization. So come up with a representation of those 16-bit integers that uses only 8 bits. So how it can be done? So problem 2, you have a string of those 8-bit integers that use your representation. So you have to recreate, okay, create the 16-bit integers as best as you can. So you will not lose any information. None of the numbers will be missing, but you have to be in an 8-bit integers. So for example, you have the source image, okay. So each of the pixel will be transformed into a code book. So code book means each of these pixels will have their own representation here. So it will be construct a code book, so that when you want to call this pixel, so you will refer to the index of 0. So once you create the code book, depending on the source image, then you will get the index of the code book. So this is the index. So this index will be saved as the compressed image. Okay, then you will have the code book. Once you do the decoded image, decompress, you are referring to the same code book. So the process of reducing number data by removing some of the detailed information by mapping group of data to a single point. So the strategy of scalar quantization, what you have to do, you have to build a code book. So with the training set, then always encode and decode with the fixed code book. Okay, so what you will do, you will understand your input data first, then from there you will build your own code book. Okay, so you have to train, okay, your input so that you can create a good code book, so that when you decode, you will use the same codebook that you built before. So most common use of scalar quantization. So build a codebook for each image and transmit the codebook with the image. So once you do the scalar quantization, so the codebook that you build will be transmit with the each image. Okay, so the train can be slow. So of course there will be a distortion. So the distortion is the difference between the input with the output. Okay, the input, okay, and the decoded image. So let the image be pixel x1 to until xt. So define the index x to be index transmit on the input. Okay, so then you will get the cj to the code word index by j. So the difference between the xi, okay, the input, with the one that you generate, okay, from the code book, so we call it a distortion. So this each of it will be, you will get the distortion. So from here you will calculate the MSE. So T is the number of pixels. So let's look on the uniform sequence scalar quantization. Let's say you have 512 times 512 image with 8 bit per pixel. So you will use 8 code words. So originally is 8 bit, so the range should be from 0 to 255. Okay, so you will divide into 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 code words. So this green will be the code word. So this is the boundary. So any pixel value from this to this will represent as this code word. Okay, so you will generate the code book. So this is the code book. So the code book will have the index and also the code word. Code word is this. So the compilation of the code book and the index, we call it as a code book. So this code book will come with the image. Okay, if you want to transmit or you want to save the image, because this code book will be called, okay, if you want to reconstruct back, okay, the input image. So this is the encoder, then you do the decoder. So the bit rate is 3 bit per pixel. Okay, and the compare ratio you can get up to 2.67. Okay, the 8 divided by 3. The second example is where you can do the thresholding. So this is the simplest method of gray level reduction, where any pixel above the threshold is set to 1 and the rest will be 0. So this turns the gray level image into a binary image. So this uniform scalar quantization can be done. So instead of simple method, which is threshold, so you can have a more versatile method, okay, by reducing the number of bit per pixel. So for example, you have 16 bit, then you want to do the uniform scalar quantization to reduce to 4 bits. So that one is more versatile, where you will reduce the number of bit per pixel. So this can be done by masking the lower bit via an operation. So the number of bits that are masked determine the number of gray level available. Okay, so this is the process. Okay, next you have alternatively, we can map the quantized gray level value to the high end of the range using an OR. Okay, this is not a sequence of process. Okay, it is a process to do the uniform scalar quantization, which is more versatile. So it can be either use N or OR. If N, then you will mask, okay, with the lower bit. If OR, you will mask with the high N. Okay, so note all mask can also be found by negating not, okay, the N mask. So the general rules to reduce 256 gray level to N gray levels by finding K, okay, such that 256 is 2 power of 8. Okay, K is 8, okay, and then equal to N. So N operation, you will mask the lower K bit with 0. 0 operation, we mask the lower K bit with 1. Okay. So you can reduce the number of gray level to any power of 2. Okay, means that you can reduce the 8 bit to 2 bit, 8 bit to 4 bit. Okay, or you can have a 120 with 32. So example 3, you have an image with 256 value. Okay, then you want to quantize to 32. So from 8 to 5 bit. Okay, 256 is 2 power of 8, 32 is 2 power of 5. So how it will be done? So first you have to find the K such that 256 divided by 2 power of K equal to 32. So 32 is one that you want to quantize. So K can be obtained by finding the bit difference between 8 minus 5, which is 3 bits. So K is 3. So then you will do the masking. Okay, mask the lower K bit. Either you use N or O. Okay, if you use N, so this is the mask. N means you will shift 3 times. Why 3? Because you want to reduce 3 bits. Okay, or you will get the vice versa of N. Okay, originally it is 1, 1, 1, 1, 1, 1, 1, 1. If you want to reduce from 8 bit to 5 bit, means you will get the difference between these two, you will get the 3. So to get the mask, you have to shift to the left 3 bit. Okay, let's say you want to quantize from 8 to 4. Then 8 minus 4 is 4. So then your mask will be shifted to the left 4 times. So it will become 1, 1, 1, 1, 0, 0, 0, 0. So if or, then it will be 0, 0, 0, 0, 1, 1, 1, 1. So it depends on how many bits you want to reduce. So if you want to reduce from 8 to 3 bits, means you have to shift 5 to the left. So you will have 1, 1, 1, 0, 0, 0, 0, 0. And the all mask will be 0, 0, 0, 1, 1, 1, 1, 1. So from this mask, then you will get the new pixel value. Okay, let's say you have this one from 0 to 255, then you want to reduce to 5 bit, which is 0 to 31. So it will be from 0 to, you will divide, okay, this interval, okay, to 8, 8, 8, 8, 8 until the end. So you will get 0 to 7. If you use N, then it will be 0. If you use all mask, so it will be 7. So since this example you are using the low end, then the new pixel will be 0.